Welcome to calculus. In this first video, we're going to introduce you to calculus by describing a couple of the problems that led us to develop calculus. And one of the big problems that mathematicians had that led us to develop calculus was called the tangent problem. And this is how we want to determine the slope of a line that's tangent to a curve just at one single point. And then the other problem was called the area problem, which is how to determine the area under a curve. In this video, we're going to start off by talking about the tangent problem. Now, in order to discuss the tangent problem, we need to do a quick review of average rate of change. And if you recall, the average rate of change is the slope of the line that passes between 2 points on a curve. And so if I'm looking at the interval, let's say generically from A to B, and I want to find the average rate of change from x equals A to x equals B, then we would take the corresponding y value for B, which is f of B, and we would subtract the corresponding y value for A, and we would divide by the difference in the x's, which would be B minus A. This represents your change in y. This represents your change in x in the denominator. Now, when we look at the average rate of change of a line, which we have 3 examples below, when we look at the slope of a line between any 2 points, that slope is going to be the same. Whether I pick these 2 points here on the first graph, that's going to have a slope of -2 because I go down 2 and over 1. And then if I pick another 2 points on the graph, let's say I pick these 2 points here, I'm going to go down 4 and to the right 2, but that has the same ratio of -2 because -4 over 2 is -2. So it doesn't matter which 2 points I pick, I'm always going to get the same slope, which in this case is the average rate of change, right? The change in y over the change in x. And it happens, the same thing will happen for the next line, right? No matter what 2 points I pick, I'm going to get the same ratio between the change of x and the change of y. Now for a constant function, for example, h of x is equal to 2 in this third graph, for a constant function, the average rate of change is always going to be 0 because the change in y will always be 0 no matter what the change in x is. If I look at the change in x between these 2 points, that's a change of 3 units, but my y value hasn't changed. I just went straight across. I haven't gone up or down at all. So my ratio is going to be 0 over 3. And no matter what's on the bottom, as long as it's not 0, 0 over something is going to give you 0. So for a constant function, your average rate of change is going to be 0. Now, if we pick a curve like x squared, depending on what 2 points I pick, I'm going to get a different average rate of change. If I call this line number 1, and I pick x equals 1, and x equals 2 as my interval, my rate of change, I should say average, I'm going to abbreviate average rate of change, ARC, for line number 1 is going to be, I'm going to go up 1, 2, 3, and over 1. So I'm going to get 3 over 1, which is 3. Now if I pick a different 2 points, let's do this in a different color so it's easy to see the difference. Let's say I pick this point and this point, and I try to find the average rate of change from -2 to 0, right here, -2 to 0. I'm going to go down 1, 2, 3, 4, and over 2. So that rate of change on the interval from -2 to 0 is going to be -2. So when you have a nonlinear function, your rate of change is going to be different depending on what 2 points you pick. Now this led to calculus. Someone said, well, what if we want to find the rate of change, but just specifically 1 point? I don't want it at 2 points. I just want it to touch the curve in 1 point. Well, in order to find the rate of change, okay, we need to do it over 2 points so that we can take the change in y and then over the change in x. So how would we figure this out if we're only doing it at 1 point? So what someone came up with, if I want to, for example, find the rate of change at, say, 0.5, specifically just at 0.5, someone said, well, what if we pick points and we estimate it by finding slopes as it gets closer and closer to 0.5? So someone took the slope of this line and then they moved closer to 0.5. Then they found the slope of that line. And then they moved closer and closer until they got so close that you could estimate really well the slope that touches at just that 1 point. Oh, this is how limits came about, because they're trying to find the limit as the change of x became 0, right? The change in x got smaller and smaller and smaller because those 2 points were getting closer and closer together. So they call that finding the limit as the change in x approached 0. So notice as I slide this point here, so the difference between those 2 points, the blue point and the green point right now, is 0.485. And then as I move that point closer, that change in x gets smaller and smaller as I approach overlapping points until it's 1 point and my change in x is 0. So we call that the limit as the change in x approaches 0. So now using that idea, we are going to find the slope of the tangent line of f of x is equal to x squared at the point x equals 1 by finding the slopes of secant lines and getting closer and closer and closer to that point x equals 1. And that change of x is getting smaller and smaller and approaching 0. So the first point that we're going to use is 2, 4. So we're going to use the point 1, 1 because that's the point we're trying to approach, and we're going to start with the second point at 2, 4. And then with the part B, we're going to move closer by going to 3/2 and 9/4. And then point C, we're going to get even closer using 5/4 and 25/16. So for part A, let's draw this on the graph. Here's the point that I'm trying to find for the tangent line, the slope of the tangent line. This is what we're trying to find, is that blue, the slope of the blue line. So for the first line that we're going to use for our estimation, we'll do this one in green. I'm going to use the point 2, 4. So I'm going to go over 2, up 4. So here's the slope of the line that we're going to find for part A. Okay, so when I find the slope of the line for part A, I'm going to take the change in my y's, which is 4 minus 1, over the change in my x's, which is 2 minus 1, and that's going to give me 3. Then I'm going to, for the next point, let's do this one in pink. I want to do the point at x equals 1.5, 3/2. So I come over to 1.5. Now I'm using this point in my x equals 1, and I'm going to try to get a closer estimate to the slope of the blue line. So for this one, I'm going to take the change in my y's, which is 9/4 minus 1 over 3/2 minus 1, and that's going to give me 5/2, which is 2.5. So that's going to be the slope of the pink line. Now I'm going to pick another point even closer. 1 1/4 instead of 1 1/2 now. So that's 5/4. So let's do orange. So now I'm going to pick this point here. Now I'm trying to find the slope of this line, which is getting closer and closer to the slope of the blue line, which is what we're trying to approximate. So to find the slope of the orange line, which is the closest line so far that we've got, we're going to take 25 over 16 minus 1 over 5/4 minus 1, and we're going to get 2.25. Now notice that I started at 3 and I went down to 2.5, 2.25. We would say the limit as the change in x approaches 0, because the change in x, which would be 2 minus 1, then 3 1/2 minus 1, then 5/4 minus 1, that change in x is getting smaller and smaller and smaller. I'm going to approximate that gets closer and closer to 2. That is my guess. If I added a 4th point and I called it 1.01, and then whatever the corresponding y value is, and I found the slope of the line that passed through that point and 1, 1, now my change in x would be 0.01, right? The difference between 1 and 1.01, again, is getting smaller. Now it's 0.1, and we would get an even more accurate picture, more accurate estimation of the slope at just the 1 point. But given the 3 values that we have here, I'm going to estimate that my slope is 2 at just that single point, x equals 1.